Hi, Nick McQuaid here, welcoming you to day 3 of iste780, Data-Driven Knowledge Discovery. And today I'll have 4 short videos. The first 3 will cover a portion of Chapter 2, pages 29 to 42, and then the fourth one will be about exercise 2.4.9. In this first one, I'd like to cover these topics here: measuring the quality of fit, mean squared error, training and test data, flexibility or degrees of, aka degrees of freedom, and overfitting. So let's get started. So this is the beginning of, this is actually section 2.2 of the textbook. 2.2.1 in particular is the subject of this video, measuring the quality of fit. And there's a very common way to do this that we're going to look at now. And there are going to be different versions of this equation that we're going to look at over the throughout the course. So this is an expression for mean squared error. And there are other expressions for mean squared error. In fact, there are other uses of the term mean squared error. So you may have seen an expression very similar to this one, perhaps with 1 over n minus 1. So this is mean squared error of the predictor, and basically what it is the difference between what we expect to observe and what we observe. And the n here is the same n as the number of observations. So we're actually summing this, finding the sum of these differences over all of the observed data. So if n is 200, then we have 200 differences between what we expected to observe and what we observed. And this observed data we're going to call the training data. And so there are 2 kinds of data that we're concerned with in supervised learning. So we're mainly talking about supervised learning here, and we have 2 kinds of data. We have training data and test data. So the training data is the data that we have available to us, and it consists of inputs and outputs for our machine. So we want to develop the best machine to find the relationship between the inputs and outputs, or to predict the outputs from the inputs. And then we would like to apply that machine to test data, that is heretofore unseen data. So it's not such a big deal to be able to predict, for example, last week's stock prices. We may have the training data may be last week's stock prices, or we may have data about symptoms and diseases that patients turned out to have. It's not that useful to predict a disease that a patient already had. What we want to do is be able to predict unseen data, or make inferences about data hitherto unseen, and we're going to call that data test data. That's the new data. We have to create the machine without having, usually without having seen that test data, and then we want to apply that machine to the test data. And here's the problem. What we would like to do is minimize the differences. In order to get the most accurate model possible, we want to minimize the differences between what we will observe and what we expect with the test data. But we only have the training data, so we could just minimize that. Hey, why not just minimize the difference between the training data and the minimize the difference between what we see in the training data and what we expect to see. And in fact, there are some techniques that are more likely to do that than others. And those techniques aren't necessarily going to work as well for the test data. In fact, there may be a significant problem with using the training data to predict the test data. The training data and the test data may differ. And the textbook uses 2 pictures to illustrate this. So let's take a look at the first of these 2 pictures right now. And both of these pictures, I have to emphasize, this is figure 2.9, this one and figure 2.10 are both pictures of simulated data. So we have something available to us that's normally not available. We know what F really is, and here F is shown in black, so F is this very dark curve right here. And we generally don't know what F is. We're only showing this we've only simulated this, and we're showing this to illustrate a point. And this is a point that applies to data that we haven't, where we don't know the true f. So anyway, this data has been simulated. So all the little circles are data that's been simulated by f. And in figure 2.10, we're going to have something similar to this, except it's a different function, and we're going to get some different results with that different function. But basically, we've simulated data from this, and there's error in that data. So the data doesn't exactly fit the function, but it sort of fits that, that function. Now, imagine that we're working with just these little circles. We don't have this black line available to us. We don't know that that's what's really going on. All we have is the training data to help us figure out what's going on. The training data consists of all these little circles. Now, it's hard to, you have to use your imagination here, because it's hard when you see this curve sitting right in front of you not to say, well, obviously that's what's really going on. If that curve isn't there, though, you don't know what's really going on. And you can use several techniques, several methods to several different kinds of machines to relate x to y in this case. Okay, and there are three machines illustrated here. The first one, the kind of mustard-colored one, I guess they call it orange. Let's see. I'm going to just zoom in on this so we can get a better look. I don't have very good eyesight. Okay, so we have a mustard-colored one, which they call orange, and a blue one and a green one. So these are these three curves, not the black curve, are what we see, and we've got this data, and we've fitted these three curves to the data using three different methods. So the orange line, I guess I'll go with their terminology. The orange line is a least squares line. So this is what we would get using simple linear regression, and these two. These other two are both spline methods, I think. I can't remember now. Let's see. Two smoothing spline fits. Okay, so these are spline methods. So these are two more flexible methods. And one of these methods is more flexible than the other. And you should be able to figure out by now which is the more flexible. Think about it for a second, and then make your bet, and then I'll say it. Which of the two? Which of these two, of the blue and the green, reflect a more flexible method? Well, of course, it's the green one that is the more flexible method, and we know it's more flexible because it fits the training data more precisely. See, it fits exactly the training data. However, the blue line, another smoothing spline, which isn't as good a fit, so it's going to have a bigger MSE than the green line, is actually much closer to reality. So if we were to simulate more data from this reality, if we were to simulate much more data from this reality, the blue line would continue to be good, and the green line might be quite awful. It might be really, really terrible because it's so conditioned on this particular set of training data. And if we ran a simulation again, these two outlier points might be over here instead of over here, and so this curve would be really useless. It would be so far away from what's really going on. And in each case, I want you to imagine the MSE based on imagining these circles, these little circles here that represent observed points. Imagine a line going from them. In fact, let's go back to, I forget what that figure number is. Let's go back to, let's see if I can find it here. Should have thought about the fact that I was going to be looking for this. Let's look at this. So the MSE is a function of these differences, the differences between what we observe and what we believe is happening. So I want you to imagine that as you're looking at the stuff. Now I have to find my place again. Whenever you're looking at this stuff, I want you to imagine all these differences and imagine what the sum of these differences is. Of course, the sum, because some are larger and some are smaller, the sum is going to come out to be around 0. But if we take the square of the sum and then take the square root of the square, then we'll have something like the absolute value, except even better than the absolute value, because mathematical theorems can be proven about it, which they can't be about absolute value. Okay, that was an unrelated thing. Okay, so for each one of these, I want you to imagine that there is a line from this circle to each of these lines, and imagine which one is going to generate the largest MSE. So clearly, for this particular training data right here, the smallest MSE is going to be for the green line, because it's so flexible, it's so well adapted to the green line. The blue line is the second best. It's going to have the second smallest, and the orange line is going to have the largest MSE for this. And so that idea is characterized in this picture here. So here we have the mean squared error as a function of flexibility. So if we get more and more flexible, this is the gray line, by the way, is the training data. If we get more and more flexible with the training data, we get a better and better fit. And we'll just indefinitely continue to do that. We'll indefinitely keep getting better and better fit to the training data. But why is it that the test data here is shaped like this? Well, the more flexible this is, the more it's going to be attuned to just this, and the more that the average errors are not, that will happen more and more as we get more data, there's a greater chance that those won't be taken into account. So although the inflexible method is the worst in both cases here, the most flexible method is only the best in the case of the training data and not the best. Clearly, we would prefer, if we knew all this stuff in advance, if we knew in advance what F really is, we would prefer this method for estimating the test data, the blue method, than the more flexible method. And this is just to illustrate the point that more flexibility isn't necessarily better. More flexibility may lead to a concept called overfitting. If we fit too closely to the data, particularly if there's a lot of variance in the data, if we fit too closely to that training data, then it's very likely that the test data will be very far away from what we predict. Now let's look at the second example. This is another example, another cooked up example. And in this example, the reality is a straight line. The reality is best fit by the linear regression curve. And the blue line is a smooth spline method that's similar. And the green line is again a smooth spline that's very flexible. So it's very tightly fit to the training data. And here again, we have a similar situation over here, except that in this particular case, the inflexible method performs about as well as one of the flexible methods. The other flexible method is really great for the training data, but just terrible for the test data. So this illustrates this concept of overfitting and the problem with having observed some data that has some inherent error in it, and knowing that when we make our predictions that the data that we're going to see, the test data, the data that we'll see after we make our prediction, that data will also have some error in it, and that error isn't necessarily exactly the same as this error. In fact, it shouldn't be. There should be some randomness to the error. If the error is not random, then we have failed to take into account some of the systematic variability. We should be able to take into account systematic variability. The variability that's left should appear random to us. The variability that is associated with epsilon, that error term, should seem random to us. That should be something that we don't think that we can really do something about. Okay, so that's it for this short video, and we have 3 more to go for today.